These are notes on statistical analysis for use when you have collected data to show whether the differences you see in your data are statistically significant or not. It's divided into 3 parts so that you can forward to the parts that you need. Part 1 is what standard error means and why you might use it. Part 2 is how to add it to your graphs using Microsoft Excel. And part 3 is how to calculate it by hand. First, we have a definition of standard deviation versus standard error. You're going to need to use these throughout these notes. I'm going to refer to them a lot. Standard deviation is how spread out the samples of a population are. So, for example, if I have a data sample where the mean, the average is 50, say I'm looking at how many jelly beans are in a jar, and I get 3 samples. One has 48 jelly beans, one has 50 jelly beans, and one has 52 jelly beans. The mean is going to be 50. But I could also have 3 jars where one has 0 jelly beans, one has 50 jelly beans, and one has 100 jelly beans. That is also a mean of 50. But the standard deviation is going to be greater where you have a larger range of data as compared to the mean. The standard error then is how precise your mean is. It's what I like to call the plus or minus factor. So if you see something that's like, it's 50 plus or minus 2, that plus or minus is your standard error. And the full term for this is standard error of the mean. Standard error and standard deviation are mathematically related to one another. You use the standard deviation to calculate the standard error. And then the smaller your standard deviation, the smaller your standard error. So the less spread out your samples are, the smaller that plus or minus factor is going to be. This now is part 1, what standard error means. Let's take a look at this graph. In this graph, we have the stomata density of lower and upper leaves on a tree. Stomata are little cells on the underside of a leaf that allow the carbon dioxide to go in and allow the oxygen to go out of the leaf. And in this study, students were looking at whether trees lower to the ground or higher above the ground on the tree had more or less stomata density, had a greater or lesser stomata density. In this graph, it appears that in stomata per square millimeter, we have a lower density of, that looks like about 22, and a higher density of, maybe that's 24.9, something like that. It appears from first glance that the upper leaves seem to have a greater stomata density than the lower leaves. However, some people might look at this graph and say, wow, those are really close together. Maybe it's not really that much of a difference. Maybe I can't really make a claim of leaves higher up on the tree have greater stomata density than leaves lower. Not to say that that bar isn't higher, but gosh, those are so close together that is less than 5 stomata per square millimeter. Is that really enough? Or could it just be a little bit luck of the draw based on which leaves I happen to collect? Maybe I collected 1 leaf from the top and 1 leaf from the bottom, and they were not representative of all the leaves. You could see where people could argue about whether this data is significant or not. Not whether the data is significant, but whether the claim that we want to make, upper leaves have more stomata per square millimeter than lower leaves, people could maybe get into an argument as to whether that is really true, which is why mathematical and scientific literacy, by the way, is so important. What standard error does is once you have calculated it properly, it adds these little error bars here. And that is, again, our plus or minus factor, meaning based on the data we collected, based on the number of trials we collected, based on the standard deviation, the sort of range. And standard deviation, by the way, is not just the range, it's a measure of the range. I'll explain it when I get to part 3. We add these little standard error bars. And what we're looking at is, or what we're looking for is overlap between the bars. So if I kind of go to, I'm going to get a pen here, go to the top of this bar here, and I drag it more or less. Oh boy, this does not look good. Over here, okay, it appears in my really terribly mouse-drawn line here, I probably could have done that a better way, that there is no overlap between these bars. Meaning that even if I have some leaves that are not quite representative of this mean, the highest stomata density in the lower leaves does not overlap the lowest in the upper leaves. If that were the full mean, that's not just taking the highest and lowest, it has to do with how it compares to the mean, how it compares to the average. Now, this, I drew a really poor line, which may or may not be very helpful. So on this graph, what I've done is I have accentuated the difference. One thing I want you to notice is that these two graphs are actually the exact same graph. And that's a little bit of your mathematical literacy. So as we said, this mean was maybe about 22. This mean was just under 25. Notice it's the exact same thing here. I've just changed this lower limit to 20 instead of 0. So it is the exact same graph. It's the exact same error bars. Those error bars are no larger than they were on this graph. If you notice here, this line comes to, again, somewhere around 23. If we notice here, this line is actually just below 23. All I've done is zoomed in. If that's confusing to you, make sure you ask, because these graphs are identical. They've just been zoomed in to accentuate the difference. And now I can see beyond a shadow of a doubt, there is no overlap in these error bars here. And that means the differences I am seeing, all things being equal, are actually significant. And I can say that there is a greater stomata density on the upper leaves of at least the species of tree that I was testing in this. That takes the question of, are these differences real or are they just chance, out of the equation. What it does is it gives us a mathematical way of saying whether or not the differences we see are actually significant or not. Now, if you are somebody who likes to go further with your math comes really easily to you, everything I've said so far makes a lot of sense, then I'm going to give you a little more. Here we have a different data set. This is surface area of upper and lower leaves. Same idea, comparing different properties of leaves on different parts of a tree. And by the way, there are some very important reasons that leaves do differ from the upper branches to the lower branches. But if we're now looking at surface area of the upper and lower leaves, and we're looking at square centimeters, this data here, these two means are actually the same. You can see that the lower leaves had an average surface area of about 92. The upper leaves a little less than 90. In this first graph, what we see is these error bars completely overlap each other and overlap the means of the other bar. So this upper here overlaps with this mean here, right? There's complete and total overlap of bars and means. That means that this difference is not significant. The difference in surface area we see, while the lower leaves did have a greater average than the upper leaves, because of these so much overlap in these error bars, That's just not a significant difference. And we need to acknowledge that and say that, yes, we saw this trend, but that difference is not significant enough to make a claim. This graph is the exact same graph with the same means, except that I've changed the error bars a little for the purpose of showing you what I'm about to show you. In this case, these error bars, and I'm going to try to do this as well as I possibly can. These error bars overlap each other, but they don't actually overlap the mean. These error bars have less overlap. They overlap each other, but not the actual means. What that indicates is that this difference may not be significant. It's not saying it is. It's not saying it's not. It's sort of a little in between, right? If we go back to this data is significant. The difference we are seeing, and I keep saying data, what I mean is the difference between the data is significant. The upper leaves have more stomata per square millimeter than the lower leaves. That is a claim we can make based on this data. In this graph, the first one here, this difference is not significant. We can say that we see this trend, but we have to qualify it by saying that the difference is not significant based on standard error of the mean. This second graph here is an in-between. It's saying we are seeing a trend where the lower leaves seem to have greater surface area than the upper leaves. However, because there's overlap in the error bars, that this data may not be significant and really more testing is needed. We should go back, we should take more trials, we should see what's going on because this is inconclusive. That is going further into a lot more math at middle school level. If you understand that there's any overlap in the error bars, so it's possibly not significant, that is good enough. This is now part 2, how to add standard error bars to your graph. This is now all of the data of these leaves on the upper and lower branches. We've got stomata, we've got surface area talked about. We also have something called specific leaf weight. Here's just a ton of data over 27 leaves, both on the lower end of the tree and on the upper end of the tree. The first thing I need to do when I make a graph is I need to get the average. In order to get Excel to calculate the average for me, I am going to put in an equal sign. Equals always means I'm about to put in a formula, and I'm going to start typing the word average. I then see average here. I'm going to double click on that, and I am going to highlight all of these numbers. These are the numbers that I want to average. I'm going to close my parentheses, and now I have my average. Now, a neat little trick in Excel is if I highlight that and I go to this tiny little green square here and I drag this over, it's going to give me the averages for all of my data. I've now made my graph of the stomata density. If you don't know how to make a graph, or you aren't sure whether to do a bar graph or an XY scatter plot, those are things that you are going to want to learn from others of my videos. But here I have a graph of the stomata density. If I were to really have this data, this would need to be 3 separate graphs, simply because the means are so wildly different from one another. A graph where I have a mean of about 23 is going to be very different from a graph with a mean of 0.03 or 90. The first thing I want to do is calculate the standard deviation. I want to do that because you need the standard deviation in order to calculate the standard error. Again, I'm going to start with equals, and I'm going to start with ST for standard deviation. And I find it right here. I want the standard deviation .p, that's for the entire population of data. Double click on that. And then again, I am simply going to highlight the data here and close that. And I have my standard deviation here. Now, to get the standard error, The standard error is actually the standard deviation divided by the square root of the number of trials you have. I'll show you that formula in a second. But in order to get it, I'm going to say equals. Then I want my standard deviation. So I'll click on it. Divided by, I put in my little forward slash. Now I want a square root. I'm going to put in SQ. And I see square root right here. And I want a square root of 26. I have 26 trials. Oh, actually, I have 25 trials because I started at number 3 here. So I'm going to say square root of 25. I'm going to close those parentheses, and I get my standard error. I now want to do the exact same thing for these 2 values here. Now, obviously, if I were making all my graphs, I could pull this all the way across, but really, I only need this for this graph here. In order to add my standard error bars, I'm going to click on my graph so that I get my chart design menu. Now I'm going to go to add chart element, and I'm going to say error bars. And I'm going to go all the way down to more error bar options. I want error bars going in both directions, and you'll notice that Excel automatically puts them in, but it puts them in on some random formula they have. That is not what we want. We want our error bars to be plus 0.78 and minus 0.78 for my lower leaves, and plus 0.87 and minus 0.87 for my upper leaves. In order to get that, I'm going to scroll all the way down to custom error bars. And then I'm going to specify the value. I get this weird table here, but all I'm going to do for that is I am going to highlight that data there. That is going to be my positive error bar. For my negative error bar going down, I just deleted what was in there, and I'm going to re-highlight this. I want this to be my positive and negative, my plus and minus value. And now I'm going to say OK. And that gives me my error bars. Finally, we get to part 3, how to calculate standard error of the mean. I actually find that oftentimes it's easier for me to calculate standard error by hand if I don't have a huge sample. The data I just showed you, I would absolutely use Excel. But if I am doing something where I have 3 or 5 trials, I generally calculate it by hand because I find it faster. I also think knowing how to calculate standard error of the mean can help you better understand what it actually is. The first part is to calculate standard deviation. Now, before you get all freaked out by this equation, it's actually pretty simple to understand. This symbol here is a lowercase sigma. It means standard deviation. This large kind of sideways M is actually an uppercase sigma. It means the sum of, adding it all together. X with a line over it is a data point. X without a line over it is the mean. And then N is your sample size. So what you are doing to get the standard deviation, you are adding together all of the data points subtracted from the mean squared, dividing it all by the number of samples you have minus 1, which gets into more statistics than you need at this point in time, and taking the square root of the whole thing. It's actually not as hard as it sounds. Let's say I have calculated how much work students are completing in each of my class periods, and I took just a random sampling of 5 students per class period. I'm going to calculate the standard deviation just for first period. So student 1 completed 93% of their work, student 2, 96%, student 3, 90%, student 4, 95%, student 5, 93%, for a mean of 93%. Now I've made myself a little table here where I just put my 5 trials here, 93, 96, 90, and so forth. Now I just do the mean, 93, minus that particular person. So 93 minus 93 is 0. 0 squared is 0. 96 minus 93 is 3. 3 squared is 9. 90 minus 93 is negative 3. Negative 3 squared is 9. 95 minus 93 is 2. 2 squared is 4. And then we get our 93 again. That's 0. I've now completed each of these mean minus point squared. Now I just sum them up. I add them together. 0 plus 9 plus 9 plus 4 plus 0 is 22. I've now completed this entire part of the equation. For part 2, this is the same table that I just explained. Now I'm going to, and then here, this 22 is the sum of these. Now I'm going to get my n minus 1. I had 5 trials. Minus 1 equals 4. I'm going to now divide my 22, so my numerator, by my denominator. 22 divided by 4 is 5.5. I'm going to square root the entire thing, and that gives me a standard deviation of 2.3. And you can see if I had the same mean, but a larger spread of data here, then that would cause this number to be greater, which would cause my entire standard deviation to be greater. So the greater the spread of your data, the greater your standard deviation. Now to calculate the standard error for period 1, I use this equation. All variables are the same as before. We're not going to switch variables on you. So this is my standard deviation. This is essentially the standard deviation of the mean, which is what we call standard error of the mean. And you divide it by the number of trials. So period 1's standard deviation was 2.3 with 5 trials, an n of 5. Therefore, 2.3 divided by the square root of 5 equals 1. My standard error is 1, so I would put my error bar up 1 and down